In this video, we're looking at error propagation or error analysis for the bridge problem, where we dropped a stone off a bridge and timed how long it took to hit the water below. So we've got our function here that physics tells us that the distance is 1/2 times the force of gravity, g, or acceleration of gravity, times the time it takes for the stone to fall squared. We've got g set to 9.8 for Earth, and then we've got that curve there. Let's show the center value. So the time we got on the stopwatch was 2.1 seconds, which corresponds, if we go up to the curve and over to the y-axis, to a value of 21.6-ish meters. But we know that there's some uncertainty in the measurement, so we said there was about a plus or minus 4 delta x value. And then, so delta x is shown down here in the green band, and we said that was 0.4. And then if we put in vertical bands corresponding to the center point plus delta x and the center point minus delta x, follow those up to the curve and over to the y-axis, that's computing our true new y values and the true delta y values from the 21.6-ish to the upper end and lower end there. And we said, hey, those aren't quite the same, 9.01 and negative 7.44. Or you could think of it as positive 7 if you want to think of distance. And that's because the function we're dealing with is not perfectly linear. And so is there a faster way to compute these delta y values? There is, and that's what we talked about in the previous video. So we can show that by showing a tangent line approximation here in black to the red curve. And then we also follow the c plus delta x and c minus delta x lines up to that tangent line approximation, and then over to the y-axis. That's the dotted horizontal lines here instead of the dashed. And then we can show what the approximate dy value is of those dotted lines from our center line. And they are the same both times here, and we can show the calculation of that. dy is f prime at our center value times dx. We get that 8.232. Or if you want to do this, the derivative by hand instead of using Desmos's derivative feature, you can say the derivative of our 1/2 gt squared is 1/2 g times 2 times our center x value, and we get the same 8.232. And we can show that if we make dx smaller, then the true delta y on the positive side and negative side get closer to each other, and it becomes a better, the dy becomes a better approximation for delta y. So why not just compute the true delta y values directly? Well, in higher dimensions that can take a long time, so this is a lot faster in general as a technique. And if you're propagating it through lots of different formulas, you take this value, move it through this formula, take that result, push it through this other formula, take that result, push it through this other formula. That can take a lot of time. You might want just a linear approximation each time. We've been doing this for a physics kind of problem, 1/2 gt squared, but in the homework you might be dealing with things like the volume of a sphere, or the volume of a cone, or volume of a cylinder. So you should Google formulas for those to make sure you have those correct. There's also a page near the back of the book, not the very last page, but like 3 or 4 pages from the back, called Areas and Volumes, and that is a good reference.